Hello, this is Deborah Barrett with the Cincinnati State Physics Department presenting the fourth video in a series on momentum. This particular video will focus on impulse. We have already realized that momentum is conserved, so the total momentum of a system stays constant if it's isolated from outside forces. That means a force must be applied in order to change the momentum of an object or a system. And that force must inevitably last for a certain amount of time. The longer the force lasts, the greater its effect. Since the acceleration ends as soon as the force ends, you have to maximize the duration of the force to maximize the resulting acceleration. And that's why the longer the force lasts, the greater its effect. That's the reason that coaches tell ball players to follow through, to maximize the duration that the force is applied, and that maximizes the acceleration, which is the effect you want from a force. In this video, we introduce a new term that incorporates both the force amount and its duration. Impulse is defined as force times duration, or impulse equals force times delta t. On screen, I've used the definition symbol instead of just an equal sign because this is, in fact, how we define this term of impulse. Well, it turns out that impulse, or force times the time interval, will be equal to the change in momentum. And the change in momentum can be thought of like any other delta in physics as being the value at time 2 and then subtract the value at time 1. Notice we are continuing to use the little arrows above each of these symbols that need to indicate directionality or vector nature. Well, it turns out that impulse equal change in momentum is actually just a souped-up version of Newton's second law. Let me show you how we get there. So here's our relationship. Impulse defined as force times change in time equal to change in momentum, with the change in momentum equaling the momentum at time 2 minus momentum at time 1. What I'm going to do is use the portion about F delta t and the P2 minus P1, and what I want to do is expand the P2 using the fact that momentum equals mass times velocity. So I'm going to take the mass of the object at time 2 times the velocity of the object at time 2, which would give us the momentum at time 2. And then I'll subtract the mass of the object at time 1 times the velocity of the object at time 1, which would give us the momentum of the object at time 1. Now, what we have is just a restatement of the relationship we already had, but what I'm going to do is assume that the mass of the object stays the same. So if the mass at time 1 is equal to the mass at time 2, in other words, if the object's mass does not change, then that means we have force times time interval equals mass times the velocity at time 2 minus the same mass times the velocity at time 1, and that means we can divide out the mass, or factor out the mass, and get velocity time 2 minus velocity time 1. Well, the short way to say velocity at time 2 minus velocity at time 1 is to say delta velocity. So we have force times time interval equals mass times the change in velocity. Next, I'm going to divide by the time interval. If I do that, I have force alone on the one side of the equation, and I have mass times change in velocity divided by time interval on the other side of the equation. And I'm realizing I forgot to put my velocity arrows in, or excuse me, my force vector arrows in, so I'm going to go back in and put those. Returning to my final equation, I want to think about what change in velocity divided by change in time is. And you and I both know that change in velocity divided by change in time is acceleration. So what we have is that force equals the mass times the acceleration, or Newton's second law, that force equals mass times acceleration. And this is going to be true as long as the mass stays the same for the object. What this shows us is that this impulse equals change in momentum relationship that we had originally simplifies down to the Newton's second law that we've already learned if we have the mass stay constant, which is why I said that the impulse momentum relationship is like a souped up version of Newton's second law. Going back to the momentum synthesis notes, we have this implication that the impulse equals change in momentum relationship is most useful if you're looking at one object and how its motion changes. It's also very helpful if you're looking to deal with force or time, but especially this version is useful if you have your mass of your object changing. You have just seen that Newton's second law, the way we've learned it before, works fine if the mass stays constant, it's equivalent. But sometimes the mass of your object is changing. For example, if you're talking about a comet, or if you're talking about a rocket, or even an airplane, its mass drops as the plane flies along because it burns up fuel. This best use of impulse equals change in momentum contrasts with the best time to use conservation of momentum. Conservation of momentum is best to use when you're looking at the motion change for more than one object, as opposed to impulse equals change in momentum, which is most useful when you're zeroing in on one object and how its motion changes, or once again, if you're looking at force or time, particularly when your mass is changing. This pretty much covers the basic idea of impulse and how it relates to momentum. Please notice before we close that impulse is not equal to momentum, it's equal to the change in momentum. Thank you for watching the video on impulse.